Hi and welcome. I'm trying to learn electrical engineering today, electrical energy, and after we've done that, we're going to do standing yoga. And if you participate in the standing yoga, then es werdet ihr alles. An electric current gives up energy as it flows around a circuit, and its capacity or potential for doing work in this way is measured by the potential difference applied to cause the current to flow. I don't really understand it. There is a potential difference applied, so that it is flowing, and while it is flowing, it is giving off energy, and measured is it the amount which it has as capacity or potential work to do, coming from the applying of a potential energy which makes it to flow around while it gives off energy, can be measured. It is essential to realize that when we talk of using an electric current, in no sense is the current destroyed, made smaller, or used up. While a current of 20 ampere flows into my house from the supply cable, at the same time a current of 20 ampere flows out of the house on its way back to the power station. Okay, they're saying it is not used up. If 20 ampere coming into a hypothetical house, it goes from the hypothetical house again out. So we use the energy carried to our homes by the current flowing through our various electrical appliances. The energy is carried out, and the amount which was carried out is what has went through it. In this book, we have considered 3 ways in which we can use this energy. The 3 possible kinds of energy conversion are: number 1, electrical energy can be converted to chemical energy by removing active chemical elements from their less active compounds. Let's read the next sentence. Also, the energy might be stored in secondary cells for future reconversion to electrical energy. This kind of energy change is seldom required in our house. So it can be stored. It can be converted electrical energy into chemical energy in a battery, be stored there, and then converted back from the chemical energy into electrical energy. The first sentence: electrical energy can be converted to chemical energy by removing active chemical elements from the less active compounds. Number 2, electrical energy can be expended in setting up magnetic fields which in turn produce motion. Every home contains electric motors. Clocks, carpet cleaners, refrigerators, and washing machines all employ electric motors. So the electrical energy is expended by setting up a magnetic field, which makes then motion, which could be used in an electric motor, a clock, a carpet cleaner, a refrigerator, and a washing machine. Number 3, electrical energy can be converted to heat energy. So out of electrical energy can be made heat. Often this is just what is required, as in an electric fire or electric cooker. Sometimes the heat is not required, as for example in the coils of an electric motor, where the heat has to be deliberately led away to the atmosphere and is wasted energy. So the electric energy is converted into heat to make water warm, for example. Next thing, the energy liberated by a current, as indeed is the case with all forms of energy, is measured in joules. So it is liberated. There comes the electric current in and it goes back again. But the energy was not used up, but was converted, or in other words, liberated. It is no longer there. But why are not 20 amperes going back? And the amount which is liberated is measured in joules. The rate of energy conversion is called power and is measured in watts. So what was coming away is called watts, or joules per second. We have provided various equations to enable this energy or power to be calculated. A joule is quite a small quantity of energy, and in everyday life a much larger unit, the kilowatt hour, is used. The kilowatt hour is usually referred to as a unit, short for the longer title Board of Trade unit. Kilowatt unit is just a way to measure how much energy was liberated. Power in watts equals VI or I2 or R. V is the potential difference in volts. R is the resistance in ohm, and I is the current in amperes. T is the time in seconds. So the power in watts equals the potential difference multiplied with the current in amperes. The work done in joules is the potential difference in volts multiplied with the current in amperes multiplied with the time it took. And the heat produced in calories, which is also the measurement there, is the potential difference in volts multiplied with the current in amperes multiplied with the time divided by 4.2. A unit of energy is used when power is consumed at the rate of 1 kilowatt over a period of 1 hour. Yes, 1 kilowatt used 1 hour long is a kilowatt hour. And it's just the same as 3,600,000 joules, as we explained on page 8. This is of course what the consumer has to pay for. The energy used, and when the electricity board charge to something, it can't be dollar, I think it's Edward Arnold Publishers Ltd. London, 1968. Great Britain. 2D. Charges 2D per unit weight are supplying the user with 3,600,000 joules of energy for 2D. This method of payment will be clear from the following examples. Example number 1. What is the cost of using a 100-watt lamp for 20 hours if the charge is 2? What are they? Pound? Pence? What could be that? $2 per unit. 2 pence? There we have it, 4 pence. So 100 watts for 20 hours equals 2000 watt hours, I think was it. And 2000 watt hours equals 2 kilowatt hours. And the cost of 2 kilowatt hours of energy are 2 times 2D. An example of is 4 pence. Is D the short for pence? Okay, they say 1 kilowatt hour costs 2 pence. And if someone has a 100 watt lamp burning for 20 hours and pays 1 pence for 2 kilowatt hours, then we would have used after 20 hours 2 kilowatt hours, which would be 4 pence. So for 10 hours, 5 hours, 1 pence. So we're saying here that 1 watt lamp could burn for 5 hours for 1 pence. 1968, I don't know whatever that all means, and it is an example. Example number 2. An immersion heater has a resistance of 25 ohms. I don't know what an immersion heater is. And is used on a 200 watt main supply. If it is used for a period of 5 hours, how is it working? Do we mean the 20 ampere are going only back if it's nothing used up? How is it going with the electricity? Is it water is standing in the pipes and the water is not flowing back? How is electricity going? Is it just going through and only if someone takes something off? And when only the amount of which is taken off goes away? How is it going with electricity? Now, an immersion heater has the resistance of 25 ohms and is used on a 200 watt main supply. If it is used for a period of 5 hours, the cost of the electrical energy used is 2 S8D. What is the cost of 1 unit? The power equals the potential difference in volts squared divided by the resistance in ohms multiplied with watts. The power is 200 times 200. Why? Because it's the resistance in ohms 200 volt times 2 squared. 200 times 200 squared, not times 2. Divided by the resistance in ohm at 25. These are 1600 watt. The energy consumed are 1.6 times 5 hours long. kilowatt hour. So we know it uses 1600 watt. And the energy under 1.6 times 5. Where do we have 5 from? It is going 5 hours, but what has it to do with 5 kilowatt hours? No, whatever. And these are 8 kilowatts. The cost per kilowatt are 32 pence divided by 8. Why is it now a completely different price as previously? The cost of 1 unit, it costs in totally 32. I don't get it. Something I will calculating out. We will find that out. If you're here for electrical engineering, you can go directly to the next part, where we're going to read on. If you stay here and participate in the standing yoga as well at your own risk. The feet are standing together, reef and the arms up. Out and down. In and up. Out and down. In and up. Out, open to the other side. In and up. And out, open to the other side. In and up. And make an inch of space between the feet. Open again to one side. In and up. And out and sink a bit down. In and up. Out, open to the other side. In and up. Out again a bit down. In and up. And out and lean onto the knees. Reef again in. And out, make a hill with the back. In middle. Out, make a belly. In middle. Out the hair. In middle. Out the belly. In middle. And out come with a round back up. Back at the top of backwards. And breathe in the arms up. Come up onto the box. And breathe out and sink down. This can go onto the knees. In and up again. Out and down. In and up. Out and down. Hands down, heels down, feet together. Breathe in, bend the right leg. Out, stretch the left leg. In and change. Out, stretch the right one. In middle. Out, down. Right hand to the sky, bend the left knee, look to the sky. Handing it. Left hand to the sky, bend the right knee, look to the sky. Hand down. Make a hand with space between the feet, shift away to the heels, breathe in and come down. Out and up again. In and down. Out and up. Take hold on the elbows and gently rock from side to side. Hands again down, feet together, breathe in halfway up, straight back. Out and down. In halfway up, straight back. Out and down. In and up. Hands together and down. The toes are pointing to the outside. In the arms up. And out, sink down. Elbows against the insides of the knees. Breathe in and straighten up. And out and come with the back up. Breathe again in. Out and down again. In and straighten up. Out again with the back up. Again in. Out and down. In and straighten up. And out comes slowly in one straight line up. Hands again down. Have the feet standing together. In the arms up. Out, lean back with long arms. In and up. Intertwine the fingers and reach high. Breathe out and reach in front. In and up, change intertwining. In and in front. Out and in front. In and up. Out, lean back with long arms. In and up. Out, lean back with long arms. In and up. Out and down with hands. In and up. Out and down. In and up. Out and down. And a bit more impulsive. In and up. down, lift up, out and down, and in and up. Bring the hands to touch and lower the hands down to heart center. It was a standing yoga. I thank you very much and until next time.